Hello guys, welcome to the physics lesson. This is the physics lesson 14. In today's lesson, we'll be looking at the nuclear fission and fusion. Nuclear fission and fusion. So what is nuclear fission? So nuclear fission is the splitting up of heavy and stable nuclei when bombarded by neutrons to produce simpler nuclei and enormous amount of energy. So what is being said, guys, here is this. If you have unstable nuclei or heavy unstable nuclei, then that heavy unstable nuclei is hit or bombarded by neutrons. Then that heavy unstable nuclei splits up into simpler nuclei and producing enormous amount of energy. Then that reaction, we call it nuclear fission. For example, the nucleus of uranium-235 splits into two lighter nuclei and 2 or 3 neutrons when bombarded with a neutron. Alright, so this is what is being said here, guys, that if we have a nucleus of uranium-235, this one can split into two simpler nuclei or 2 or 3 neutrons and when bombarded with a neutron. So this can be shown below. So let's say we have this uranium-235 92, then is bombarded by a neutron, which is NO1. Then this one now splits into two simpler nuclei, one barium-14456 plus then krypton 9036, then plus also 2 neutrons, then also releasing energy. So this is now a fission reaction where on the right side you have a nuclei being bombarded with a neutron. Then on the right side you have two more now nuclei, and then you have also a neutron and also energy. So this is a fission reaction. So these two here are known as the fission fragments. Alright, so let's push this one up. So what we are saying here is this, that the neutrons from this reaction can bombard other uranium atoms, causing them to split also, setting up a chain reaction in the process as shown. So what we are saying is this, that the product, these neutrons, can still bombard other uranium atoms in the same sample where this one is. So when one uranium here is bombarded by a neutron, and then it splits into these simpler nuclei, producing also 2 neutrons and the energy, these can also still bombard other remaining neutrons or nucleus of uranium in the sample, splitting them also. So we are saying that the neutrons from this reaction can bombard other uranium atoms, causing them to split also, setting up a chain reaction in the process as shown. So this one now can cause a chain reaction where now, for instance here, one neutron bombards this uranium-235, then this one splits into these we are calling fission fragments, which are these, and others, this one here, then this one here, then releasing these 2 neutrons and some energy. Then these neutrons can still go and bombard other uranium, and this one, when it goes here, again splits this one into nuclear fragments, and then also here this neutron here, which is called the fission neutron, also can bombard another one, another uranium, and then also this one splits, producing also fission fragments, and then this one also can release 2 neutrons. These 2 neutrons also can still bombard other uranium nuclei, also producing also energy and other neutrons. So this reaction can go on until all the uranium nuclei have been split. So such a reaction is what we call a chain reaction. All right, so let's look at the nuclear fusion. So what is nuclear fusion? We are saying nuclear fusion is the joining together of lighter nuclei to form a heavy nucleus and production of enormous amount of energy. So we are saying nuclear fusion is the joining together of lighter nuclei to form a heavy nuclei and the production of enormous amount of energy. So here it's opposite. In this situation now, there are two or more lighter nuclei joining together, and as they join together, then they produce enormous amount of energy. So such a reaction is called the nuclear fusion. So we are saying such a reaction occurs in the sun when hydrogen nuclei undergo fusion to form helium nuclei and production of large amount of energy or solar energy. So in the sun, there are hydrogen atoms. So those hydrogen atoms under high temperature now fuse or join together to form helium. So as they join together to form helium, then the reaction produces a lot of energy, and that energy is what we call solar energy. So for instance, we are saying this hydrogen here plus another hydrogen here. So this hydrogen with it at mass number 2, they are called the deuterium. So if two deuterium hydrogen now fuse, then they form a helium atom like this one. Then also produce also a neutron, and then energy also is produced. This is a lot of energy that is produced in the sun. All right, so we are saying scientists have been able to perform such a reaction in hydrogen bomb, and also research is being done on the controlled fusion of isotopes of hydrogen, which are deuterium and tritium, to give helium. So what we are saying is this, that such a reaction which produces enormous amount of energy has already been done by scientists in the manufacture of some bombs called the hydrogen bomb. So these hydrogen bombs that have been created is a result of joining the isotopes of hydrogen known as deuterium and tritium, and these when they react, then they form helium, but producing a lot of energy. So such a reaction now is done in controlled amount. All right, so for instance, we are saying if this is an isotope of hydrogen known as deuterium plus another isotope of hydrogen known as tritium with mass number 3, these when they fuse, then they give us helium. This one is helium, then plus they give us a neutron plus enormous amount of energy. So such energy is called the nuclear energy. All right, so let's push this one up. Then what we are saying here is this, that the nuclear fusion requires extremely high temperatures. This is because the small nuclei require enough kinetic energy to overcome their electrostatic repulsion. Yeah. So this reaction requires a lot of energy because you understand that the nucleus of atoms consist of protons, and protons are positively charged. So for these two to come and fuse, there must be a force that should bring them together to fuse that is greater than the repulsion, because you must understand that positive repel and negative also repel. Now if these two nuclei are coming together, then they must face a repulsion because the nucleus is positive and the other nucleus is positive, so they will repel. Now there must be enormous energy or temperature to fuse them together, and as they fuse, they even produce more heat, all right, or energy. So we are saying that the energy we receive from the sun is from nuclear fusion. The sun is made up mainly of hydrogen and helium. Within the sun, the temperature is millions of degrees Celsius. There is the constant fusion of small nuclei into larger nuclei. So that's what happens in the sun. Now let's look at the activity and the half-life. So now we are looking at the activity and the half-life. All right, so let's begin with activity, which is represented by letter A, capital letter A. It is also known as decay rate or rate of decay. So depending on the book that you are using, some books may be using activity, other books decay rate or rate of decay. But all these means the same. So what is activity? So we are saying this is the number of decays of a radioactive source per second, or the rate at which a radioactive substance disintegrates. So it is just the rate at which a radioactive substance disintegrates, or is the number of decays a radioactive source per second. So like, a radioactive source or material, it is always decaying. Now, if you are trying to measure how much per second is decaying, then you are trying to find out the activity of the radioactive material. All right, so we are saying that activity, which is A, can be expressed in units of mass remaining with time, or counts per minute or per second. So it depends with the machine that someone is using. It can either be how much mass is remaining with time, or how many counts are being produced per second or per minute. And all those are ways of measuring activity or rate of decay. So we are saying now we are moving to half-life. So half-life represented by T and half. So it's defined as half-life of a radioactive element is defined as the time taken for half of the unstable nuclei to decay. So it is the time taken for half of the unstable nuclei to decay. Now, you have to understand this definition and understand it better. So, there we are saying a radioactive element is always decaying. Now, let's say you came across a radioactive element which is decaying, but at that time you came across it, you measured its rate of decay and you found it to be maybe 20 counts per second. That's how you found it. So that amount you have found, or that activity, you can call it the initial rate. So now let's say you found it at 20 counts per minute. Then after some time, you come and measure it. Then it is at what? At 10 counts per minute. Then the time that has been taken to move from 20 counts per minute to 10 counts per minute, that time is what we call half-life. Let me put it in another way. Let's say you found a radioactive substance that is decaying, but you found its mass to be, let's say, 4 grams. All right? You found it, you measured its mass, and you found it to be 4 grams. Then you leave it, and after some time, you come back and you measure its mass and find that it is now 2 grams. So now, since it has halved from 4 grams to 2 grams, then the time that has passed from 4 grams to 2 grams, that time is what we call half-life. Now, let me also put it in this way. Let's say you are popping popcorns, right? So you are popping popcorns on the pan. Let's say you have 100 popcorns that you are popping. Quite well you are popping them, right? Yes. So Now you have 100 of them. Now the time it takes for 50 popcorns to pop can also be said to be half-life of popping popcorns, because you had at the beginning 100 popcorns, then after a certain period of time, half of them have already popped, 50 of them have popped. Then that time that has passed for those 50 to pop is what we call half-life, or can be called as the half-life, as simple as that. So that's why we are saying half-life of a radioactive element is defined as the time taken for half of the unstable nuclei to decay. So it can also be defined in this way as the time taken for half of the count rate of a radioactive substance to form. Yeah, so it can be defined as the time taken for half of the count rate of a radioactive substance to form. This is why I said, let's say you found a radioactive substance is decaying at a rate of 20 counts per minute. Then after some time, you come also and measure its decay rate and find that it is 10 counts per minute. Then that time that has passed to move from 20 counts per minute to 10 counts per minute, that time is what we call half-life. All right, so we are saying, for example, if at the start of the measurement, the radioactive has 10,000 unstable nuclei, and over 2 days, 5,000 of these unstable nuclei undergo radioactive decay to stable nuclei, then the half-life of the radioactive isotope is, or of the radioisotope is 2 days, because we are saying at the start of the measurement, the radioisotope has what? 10,000 unstable nuclei. And over 2 days, 5,000 of these unstable nuclei undergo radioactive decay to stable nuclei. So after 2 days, these have already broken down from 10,000 to 5,000. Then we are going to say that 2 days then is the half-life of the radioactive isotope. So this we are saying, then the half-life of this radioisotope is 2 days, meaning after 2 days, its amount has to halve. Again, after 2 days, then if 2 days passes, this 5,000 should come to 2,500. That's how it goes. So let's look at now calculations involving half-life. Calculations involving half-life. So we are going to look at number 1, finding the half-life. So the calculations involving half-life, we are going to look at the many. 1, finding the half-life. Let's push this one up here. Then in number 2, the number of successful half-lives that have passed. So there is finding the half-life, then there's also calculation that involve the number of successful half-lives that have passed, and then 3, total number or total period of decay, which is represented by T, or the age of a radioactive substance. So total period of decay, which is T, is also known as the age of a radioactive substance. Then 4, finding the amount of decay, or finding the amount decayed or remaining. So these are the things that we do in half-life. The question can come asking you to find the half-life, also to find the number of successive half-lives that have passed, also asking you to find the total period T, or the age, or finding the amount decayed or remaining. So we are saying we can use the following 3 important equations to calculate any of the above. In fact, I never used the 3, I just reduced them to 2. The third one maybe may complicate your work. So I gave number 1 this equation which says half-life is equal to time or total period or time period divided by number of successive half-lives. Then in number 2, it is 2 to power number of successive half-lives is equal to original amount over amount remaining, or we have n 2 to power n. N stands for successive half-lives. So 2 to power n is equal to original activity divided by remaining activity. So this equation and this one are the same. It's just that sometimes you are given amount in grams, or sometimes you are given as activity where they say 10 counts per minute or 2 grams per minute. So that now becomes an activity where they are saying per minute or per hour or per year or per second. But when they say 2 grams, then that one is just the amount. All right, so now we are saying where n is original amount, n or then n just here is remaining amount, then a or is original activity and a is remaining activity. So let's look at an example. So we have this example here which says cobalt 60 has the half-life of 50 years. If the original mass of cobalt 60 is 500, find A, the mass of cobalt that remains after 15 years, then B, the time taken if 1.5 grams of cobalt remains. Then question number 2, they're saying a radioactive material gives a count rate of 8,000 counts per minute. Then after 20 days, it gives a count rate of 500 counts per minute. What is the half-life of the material? Then 3, they're saying a radioactive isotope has a half-life of 6,000 years. Then how much the time passes before the rate of emission from a sample of this isotope falls to 1/16 of the original value? So let's see how we can answer these. All right, so let's start with 1 solutions. So number 1, they're saying cobalt 60 has the half-life of 5 years. If the original mass of cobalt 60 is 500 grams, then find A, the mass of cobalt that remains after 15 years. So there are 2 things here, or 3. We have been given half-life 5 years. Then we have been told original amount of cobalt 60 is 500 grams. Then they're asking us to find the mass of cobalt that remains. So now this means that we'll use this formula here. 2 to power n is equal to original amount over amount which remains. So this formula is what we are going to use. However, we don't know n here. N is the number of successive half-lives that has occurred. So since we don't know n here, so what we are going to do here is first to find the n using this formula here. Half-life is equal to total time divided by number of successive half-lives. So when we go in this question, we are told the mass of cobalt that remains after 15 years. So 15 years is the total time. So say 15 years. Then we are told half-life is 5 years. So we'll say half-life is 5 years because we are told has the half-life of 5 years. Then n is unknown. Then here we'll make n the subject of the formula. If you don't know how to make the subject of the formula, click a video whose link appearing here to teach you how to change the subject of the formula. But if you have downloaded this video, you won't see the link here. So when we make n the subject of the formula, it will be n is equal to t over half-life. Then we'll substitute n is equal to t is equal to 15 divided by half-life is 5. Then we'll say n is equal to 15, 5 into 15, 3. So n is 3. So we'll say now here we want to find what? We want to find the mass of cobalt that remains. So we have known n now. So this one, we know it. Its original amount. So if the original mass of cobalt 60 is 500, so here it's 500. Then now this one, find the mass of cobalt that remains after 15 years. This one we don't know it, but then we have found n is equal to 3. So again we'll make this the subject of the formula, this n, the amount remaining. So it will be n is equal to NO over 2 to power n. Then we'll say n is equal to NO is 500 divided by 2 to power 3, which will give us n is equal to 62.5 grams. So if you get 500 divided by 2 to power 3, then you get 62.5 grams. So this is the answer. So let's go to another example here quickly so that we see how also to answer this one. So B, we are being asked to find what? The time taken if 1.5 grams of cobalt remains. So let's find this one. Solution as well, right? So again, they're saying we need to find the time taken. So the formula which has time is this one. However, when you look at this question, we don't know n, but we know half-life. So again, we'll find n using this formula, because we know that we have original amount is 500 grams. Then the time taken if 125 grams of cobalt remains. So what remains is 125. So n just here is 125. Then any small letter n is not known, the number of successful half-lives. Then what we are going to do is to say 2n now is equal to, this one is 500 divided by 125, which is going to give us, when you divide this one, you get 4. Then this one becomes an equation where we need to find n. So now what we are going to do to find n here is to raise or to make also this number like this one. So we are going to raise to make 4 have a base of 2. Look for a number which, when we put it as a base of 2 to power something, or in other words, here you need just to put 2, and then you say to which power can 2 be put in order to give us 4. So you find that 2 should be put to power 2 to give you 4. So you say, okay, it is equal to, here it will be 2 to power 2, because 2 times 2 it will give you 4. So now, since you have made the bases to be the same, then even the powers are the same. So if the bases are the same, the principle is that even the powers are the same. So meaning n is equal to 2. So you have known n. So n is equal to 2. Now after knowing n, so what you are going to do now is to know that half-life is equal to 5 years here. Then now t is what you want to find, because it's saying find the time taken. So what you are going to do is now to make t the subject of the formula. So t is going to be now n times half-life. So you substitute, you are going to say t is equal to n, which is 2, times half-life, which is 5. Then you say this times this, which will be 10 years. So the time now taken to move from 5,000 to 125 is 10 years. All right. So now let's move to another question. This is question 2. A radioactive, okay, let's just push it here. So a radioactive material gives a count rate of 8,000 counts per minute. After 20 days, it gives a count rate of 500 counts per minute. What is the half-life of the material? So they want us to find the half-life. So quite well, half-life is going to be T over N. So we know T has been given. They're saying after 20 days, it gives a count rate of this. So 20 days is time. Now we have been given count rate. Remember we talked about count rate. So this is activity. So original count rate is 8,000 counts per minute. Then after 20 days, you have now remaining count rate, which is 500 counts per minute. So we are going to use the other equation to find N here. This one. 2N is equal to original activity over remaining activity. So original activity is 8,000 counts per minute. I've abbreviated count, then per minute. Then A just here is remaining count rate, which is 500 counts per minute. Then N is unknown. Then you say 2N is equal to, you get AO, you put 8,000 divided by 500. Then you divide this one, you get 16. Then you look for 2. So here you have 2. So meaning here again you need to have 2 raised to a certain power. So you ask yourself, to which 2 can be raised to give you 16? So you find that it will be raised to 4. Right? So you say 2n is equal to 2 to power 4. So 2 to power 4 should give you 16. So if the bases are equal, then the powers are equal. So it means n is equal to 4 also. So you have found n now. You say n is equal to 4. And then you have total time is equal to 20 days. Then now half-life is not known, question mark. So now what you are going to do, you say half-life is equal to now 20 days divided by number of successful half-life. So when you divide this one, you get what? 5 days. So this is how it works. However, there are so many ways of calculating this one, but this one also is easier. Now let's go for the remaining question 3. Question 3 says a radioactive isotope has a half-life of 6,000 years. How much time passes before the rate of emission from a sample of this isotope falls to 1/16 of the original amount? A radioactive isotope, let's push it here. A radioactive isotope has a half-life of 6,000 years. So this is half-life. How much time passes before the rate of emission from a sample of this isotope falls to 1/16 of the original value? So they want us to find what? Time now. So as usual, the formula is this one. Half-life is equal to time over number of successful half-life. Now n is not known. So what we are going to do to find n, we'll say n is equal to original amount over amount remaining. Now, when you look at this question, is quite tricky. So they're saying how much time passes before the rate of emission from a sample of this isotope falls to 1/16 of the original value. So we have been told that the sample is falling to 1/16 of the original value. Do we know the original value? We don't know. we have only been told that of that original value, what has fallen is this of the original value. So then it comes easy for us to assume the original value. So we say the original value or amount, which is NO, let's assume it is equal to 2. Now, this one now remaining, we are going to say the amount remaining is 1 over 16 of, so of means times, so of the original we have said it is 2, so we'll put it 2. So we have said 1 over 16 of original. This is it, 1 over 16 of original. Original we assumed it to be 2. Then we'll say now equals, when we evaluate this one, we'll get 0.125, meaning n is equal to an unknown. So we have found this is this. So now we'll come here to n is equal to, original is 2 divided by n here is 0.125. So 2 to power n is equal to this one divided by this, we'll get 16. Alright, so we'll get 16. Then again, we'll look for a number which we'll look for 2. We'll say 2, to which power can we raise it to get 16, which is 4. So say 2n is equal to 2 to power 4. Then if the bases are equal, even in the powers, so n is equal to 4. Then here now say n is equal to 4. Then t is an unknown. Then half-life is 6,000. Then we are going to make t the subject of the formula. T is equal to half-life, or number of successive half-lives times half-life, which is going to be equal to n is 4 times half-life 6,000. Then we multiply, which will give us 24,000 years as the time taken, how much time passes. So this is the time that has passed. So let's move and look at what we call decay curve. So what is a decay curve? We are saying this is a curve obtained when a graph of amount of a radioactive substance is plotted against time. So when the amount of a radioactive substance is being plotted against time, then it produces what we call a decay curve. So what should make sense here is this: the amount of a radioactive substance is never constant. It keeps on disintegrating. So as you measure how much is disintegrating every minute or every hour or every second or year, then that data which you collect, how much is disintegrating against this other time, then you can come up with those values and plot them. When you plot such a graph, that graph is called a decay curve. Alright, so we are saying time corresponding to half of the original amount gives the half-life of the radioactive substance as shown below. So time corresponding to half of the original amount gives the half-life of the radioactive substance as shown below. So this sentence cannot make sense unless I draw the graph. Let's say this is the graph like this. On the vertical axis, we always put the amount, original amount, or just amount. Yeah, you start with original amount. Then on the horizontal axis, it is time. Then let's say you start at 0 time and everything. Let's say the graph that you have plotted, it always goes like this. Okay? It is a decay curve. Decay curve means it starts from high, then it goes to low. That's why it is meant by decay, meaning the amount is decreasing with time. So the other way of defining a decay curve, you can say it is a curve which shows how the amount of a radioactive sample decreases with time. Yeah, so it is a curve which shows the decrease of the amount of a radioactive substance with time. So with time, if this was the original, then as time passes, you find that the original also starts decreasing like that, exponentially. So if this is the graph that has been plotted, this is the original amount. Remember, this value is being used for original amount. So if we divide this line into the middle here, and then it means we have divided the original amount. So it means original amount divided by 2. So if we get a line from here on the middle, we go to the graph. When it touches the graph, we go down. Then this value will get on time here. We call it half-life. It will be half-life. That's why we are saying time corresponding to half of the original amount. Half of the original amount is this one. So when we go here, this is the time corresponding. So the time corresponding to half of the original amount gives the half-life of the radioactive substance as shown below. So this is what I was saying, you understand later. So again, if we get this one, we divide it by 2 again, like here, then it will be n/4. If we get a line that comes here and we come down here, then we'll find another half-life, which we are calling half-life number 2. So the half-life you get here and this one here, it is the same. So the time from here to here, it will be just the same. However, from here to here, it is as good as getting 2 times this one to arrive at this one. So we are saying that the half-life of a radioactive substance is constant, and as it can be seen from the graph. So the half-life of a radioactive substance is constant as it can be seen from the graph. So it is constant from here. If it took 2 seconds to move from here to here, it means even from here to here it will be 2 seconds. If we divide again here, where we get n/8, we come, maybe it touches here, it goes down there. Again, it will be 2 seconds that will pass. So now let's look at an example. So we have this example here where we are saying a Geiger counter was used to measure the activity in counts per minute from a radioactive sample in the laboratory over a period of years. Over this period, the background radiation was regularly measured at 4 counts per minute. The table of results is shown below. So this is the table of results. So in this table, it has these columns: time in years, then recorded count. So we have at 0 years, 1 year, 2 year, 3 year, 4 year. Then they recorded activity. At 0 years, it was 35. At year number 1, it was now, after 1 year passed, it was 20 count per minute. After 2 years, 12 count per minute. After 3 years, 9 count. After 4 years, 7 counts. Then activity due to sample alone. Here they are saying it is 30. So the point they are making, guys, is this. They are saying over this period, the background radiation was regularly measured at 4 counts per minute. It means in these values there was also background radiation, which is radiation that does not come from a radioactive source. This is the radioactive that comes from the environment. So this radioactive, which comes from the environment, was measured together with that which came from the source. So in finding activity due to sample alone, then you need to subtract 34 minus 4 to get 30. All right, so here now they're saying, 1, copy in your answer booklet and complete the table giving the activity of the sample alone. So they're saying you copy this one. Since it was an exam paper, I just altered some values here. So they said they copy this one and then they do what? Complete the table giving the activity of the sample alone. So needed to complete here. So if they said 34 minus 4 to get 8, I mean 30, then here you say 20 minus 4 to get 16. Then here also 12 minus 4 to get 8. Here 9 minus 4 to get 5. Then here 7 minus 4 to get 3. Yeah, that's how it moved. So now this is done. That's how it was supposed to be completed. Now on a graph paper, plot a graph of the values of the activity of the sample alone against time. So you plot now the value of the activity here, the values of the activity alone against the time here. So this is what we are going to do to plot this on a graph. And most of you have been emphasizing you needed to know how to plot. So we are going to come to this part. We get the table, put it here, we bring the graph here. So on this graph, the first thing that you need to know is to give it a title, which is what you are doing. You are plotting activity against time. Then you need also to label the axis. So if you have activity against time, then the vertical axis should be activity, the horizontal axis is always time. So you say activity, I've just abbreviated, is A in counts per minute, then time is in years, because time is in years. So this is activity due to sample, which is count per minute. I've just gotten A for activity here, then open bracket C for count, then slash MIN for minute. Now the next thing that you should do is to put a 0 here. Alright, so now after that you started drawing the line to demarcate a line so that you see how it is going to move. Now the next step, guys, is very cardinal. So you need to make sure that these values which you are plotting, time and the activity, fit on the vertical and horizontal axis. So time, which is 0, 1, 2, 3, 4, should fit well on the horizontal axis. So how? Since you have enough space here and you only have 0, 1, 2, 3, 4, then you need to choose 10 boxes to give 1 unit. So if I choose 10 boxes, then I'll draw a line here. After 10 boxes, another line. After 10 boxes, another line. After 10 boxes, another line. Then now I'll give, since this is 0, the second line will be 1, the other one 2, the other one 3, the other one 4. Then I'll shift. I'll also make a line here. Then I'll come to these which I need to put here. They must fit here. So I have the largest value is 30, the smallest is 3. So I'll also study this one and see how they can fit these. So I can put them in 10, 10. So from here to here, I'll get 10, draw a line, after 10, a line, after 10, a line. Then I'll say, I'll give them in 10, 10. I'll say this is 10, 20, 30 to cater for what I have. Then now I'll start plotting 0, 30. So 0 is the x-axis. I'll start from here, 0, then 30 is on the y-axis, which is the activity. So I'll say 0, 30. I'll move from 0 to 30. I'll put a point there. Then I'll shift 1, 16. 1 is here. I'll go to 16. So if this is 10, 11, 12, 13, 14, 15, 16, put a point there. Then I'll come here 2, 8. So this is 2. I'll go to 8, 0, 1, 2, 3, 4, 5, 6, 7, 8. So 8 will be here. Then I'll go 3, 5. 3 is here. I'll say 1, 2, 3, 4, 5. Then I'll say 4, 3, 4, 3. So 4, 1, 2, 3 here. Then I'll draw a smooth line like that. So after drawing this one, you are done with this one, which can give you 4 marks. These 4 marks. Then the last question is saying, from the graph, determine the half-life of the sample. So to determine the half-life, you only come 30, you divide 30 by 2. Original amount, you divide it by 2 to give you 15. So you come on a graph here to find 15. If this is 10, 11, 12, 13, 14, 15, then you draw a line to go this way. When it touches the graph, you follow it down again. Then where it touches, that's where you read the time from. So if this is 1 and this is 2, then it is moving as 1, 1.1, 1.2, 1.3, 1.4, 1.5, 1.6, 1.7, 1.8, 1.9, 2. That's how it is flowing. Now you are not reading everything. I'm just showing you so that you understand. So now what we mean here now is this. So from here now, it will be 1.1. 1.1. So your half-life, you are going to say half-life is equal to 1.1 years, because time is in years. So we are done. So let's move now to uses of radioactive substances. So radioactive substances have got a very important uses. One of them as tracers. So we are saying the movement of radioisotopes can be detected and traced. So the movement of radioactive isotopes really can be detected and traced. So we are saying safe and small amount of radioisotopes can be used to 1. Check the functions of body organs using iodine 125. So the fact that we can detect radiation and also trace it is very cardinal. So remember, we talked of the gigamolar counter, the gigamolar counter, that is the most important tool. So which is able to detect radiation. So radiation can be passed either in water or in a body, and as it is passing, another instrument called the detector can still detect it. Now because of that, we can able to trace the way radiation is moving either in the body or in trees or in water in a pipe. So because of we can able to trace it, so we can use it. Safe and small amount of radioisotopes can be used to check the functions of the body organs using iodine 125. Also, tracking a plant's uptake of fertilizer from the roots to the leaves. So when radioisotopes are mixed with the water and fertilizer put in the soil, then the radioactive or radioisotopes together with the fertilizer can be absorbed by the plant and be moved. So as it is moving, it can be traced how it is moving into the plant. Then 2, detecting leakage in underground pipes. So whenever underground pipes are happening to develop leakages, we can still use radioisotope atoms to trace the leakage or detect the leakage by just injecting small amount of a radioisotope into the water. Then above the water, a detector moves, scans the radiation. When radiation is detected above, then it will show that it is leaking from a certain leakage in a pipe. Then we are saying that a radioisotope with a short half-life and emitting gamma rays is used to ensure that radiation is not emitted for too long, and gamma rays are easily detected outside of the body since they are very penetrating. So what is being said here is this: if you are using a radioactive material to detect leakages, then you need to use a substance or a radioactive substance with short half-life because if you use one with long half-life, it may end up after you have done your job remaining in the water. So what you should do, use a radioactive substance that have short half-life, so that once it detects, it finishes its job, then all its material should decay and finish. And then you need to use gamma rays, because they'll have stronger penetrating power to be detected above the soil. Then two, we are saying it is used also in radiotherapy. So we use radioactive substances in radiotherapy. We are saying this is the process of using radiation in the treatment of cancer. So radiotherapy is the process of using radiation in the treatment of cancer. So we are saying this uses cobalt-60, which is an isotope that is a strong gamma rays which are directed at cancer cells to kill them. So we are saying this uses cobalt, which is an isotope that now produces strong gamma rays which are directed at cancer cells to kill them. Yeah, so now gamma rays from cobalt-60 can be directed on a radioactive substance, so that radioactive substance now can be directed on cancer cells, so that the cancer cells can be killed. So again, this is how it is used. Then here we are saying it can also be used, the radioactive materials can be used in thickness control. So here we are saying radioisotopes are used to control a steady thickness in some production techniques, like paper production or steel production. So paper production, or papers have got a certain thickness, right? So that thickness is controlled using a radioactive material. So this is the process which happens. So here you have what are called rollers. Then here you have a detector. Then here you have a beta source, a material producing radiation. So if a paper is coming from this way, it finds rollers. Rollers now will press it or compress it into a certain thickness. When it passes here, radiation coming from a beta source passes here, comes this side, and then if this radiation which is detected here is according to what was set for the particular thickness, then this one will continue going nicely. But if it is detected that the radiation here maybe has increased, then it means here the thickness has decreased as well. So meaning, if the thickness has decreased, then this one will send information to say, no, there's too much radiation coming, meaning you have reduced the thickness. So this one will be told, no, can you adjust the rollers to move apart? So these rollers will move apart to give a certain thickness. So, but if, let's say, as radiation passes come this side, this radiation becomes smaller than what was set for a particular thickness, then what will happen if this detects the smaller radiation, it sends to these rollers, informs them to say, no, the thickness has increased, that's why little radiation has reached here. So these rollers will be told to move closer so that they can compress the paper more. So that's how thickness is controlled. So here we are saying if the paper from the rollers become too thin, more beta radiation reaches the detector. So more beta radiation will reach the detector. Then signals are sent to the control unit. This is the control unit, which adjusts the gap between the rollers. So we are saying the use of beta emitting radio isotope with a long half-life is needed to ensure that the paper remains at the same thickness. So here you need to use a beta radioisotope which is emitting beta. because beta cannot be stopped by a thin of paper. A thin sheet of paper, it cannot stop. If you use alpha, alpha is not suitable because it will not be able to penetrate to come here. If you use gamma, gamma is not suitable because gamma, no matter how much the thickness is going to be, it will penetrate and you continue recording the same thing here. So beta is the best radiation to use, because if the thickness starts increasing too much, it may be blocked. At that time, you'll be able to change the sizes. And then the half-life of the source of beta should be a bit longer so that it can allow you to finish the process of making the thin sheet, the paper. So another use of radioactive material is in carbon dating. So carbon dating, we are saying this is the process of estimating the age of old fossils. So the process of estimating the age of old fossils is what we call carbon dating. So how does this work? We are saying the amount of carbon-14 in plants and animals stays constant when the plant or animal is alive. So you need to pay attention, guys. This is quite tricky and advanced. So this carbon-14 here is a radioactive material. So as long as a living thing is alive, then this amount of carbon is the same, remains the same size in the body of the living thing. So get this principle. Then we are saying, however, once a tree has been cut, so we are dealing with a tree, once a tree has been cut, the carbon-14 decays and its activity drops over a very long period of time. So because carbon-14 years has a long half-life, so even when it is decaying, it takes long to decay. Now, the issue is this: when the tree is cut, it means the tree stops absorbing extra carbon-14 from the environment. Now, since it has stopped absorbing, then what it means is this, that this carbon-14 which it has already starts now decaying because it is radioactive. It doesn't stay the same. Now, as it is decaying, we are saying that the activity of the artifact, now we are using the word artifact, which is a sample. The activity of the artifact sample, in this case the tree that has been cut. So the activity of the tree can be measured and compared to what it would have been originally, and in this way the age of the artifact or the tree can be determined. So what is being said is this, so simple, guys, to understand. What is being said is this: if we are saying, let me give you a scenario. If the tree, when it is alive, the original count rate is what? Let's say it is always 40 decays per minute, let's say. That's what its count rate always is. Now, after they cut it, it starts decaying, because this amount now will start decreasing. Maybe they find that now what has remained in that thing after they cut, maybe it is 14 count per minute. Here I didn't put count, so let's say count. Here also count per minute, right? So count per minute. Then they'll compare this and this to know the age. Remember, if they already know the half-life of this carbon, let's say the half-life is already known to be 50 minutes. Let's just assume it's 50 minutes. That's its half-life. 50 minutes. Then remember we had these things where we said 2n is equal to a 0 over a. So now we can use this equation to find the n. So we can get this original put here, this one put here, then find the n. After we find the n, we know now this formula which said half life is equal to we said t over n. So this one becomes time, which can be the age. So we can know the age. So we make this the subject of the formula t. It will be equal to now half-life times now what? N. So this way we can know the age. This is how scientists are able to estimate the age. When they tell you the age of the Earth is about 5 billion years, they are using carbon actually 14 or 12, carbon 12 to do that, and that's how it works. So the other use of radioisotope material is in sterilization. So we are saying food and chemical equipment like surgical instruments, bandages, and plasters can be kept free from germs and bacteria by using gamma rays. This is called irradiation. So those materials which are used at the hospitals, they are supposed to be safe. So they keep them in a storage where radiation is always radiated on them to kill any bacteria so that they remain safe. So that process is what is known as irradiation and its sterilization. So another use of radioactive material is in smoke detectors. So we are saying radiation isotopes or radioactive isotopes which emit alpha particles can be used in smoke detectors. So we are saying streams of alpha particles can be sent across to a sensor from a sealed alpha source. In case of the presence of smoke, the smoke particle blocks the alpha particle from reaching the sensor, thus triggering the alarm. So let me explain. If this is the house, above in the ceiling board, they get here something like there will be a source of radiation here which emits radiation. Then on this side there will be a detector. So now this radiation always passes and reaches the detector. So the detector will be quiet as long as the radiation is moving from the source reaching it. Now if there is smoke that is about to cause fire, if smoke passes here, the smoke is going to block this radiation from reaching there. Then when it blocks, this now detector will trigger an alarm to sound to say something has blocked this thing from reaching. So it could be smoke. That way a human being can be alerted and can take actions. So this is what has been explained here. So we are saying that the long half-life is useful as it ensures a continuous source of alpha particles, meaning the detector is very reliable and will not stop functioning. This one should have been americium 241 has a half-life of 432 years and is a good source of alpha particles. So in this case, in a smoke detector, what should be used is an alpha particle, because an alpha particle now is able to pass through smoke. I mean through the air. But it can be stopped by smoke. But if you use a beta cannot stop smoke. So if you are using a beta here, where this radiation is passing, and this radiation is for beta, even if smoke passes here, this smoke cannot stop it. It will continue moving and it will not make you sense anything. So the building can burn. So meaning you need alpha, which when smoke passes, it cannot go because it has less penetrating power. So again, you need a half-life which is longer, because a building need to be safe for as long as it exists. If you use a short half-life material or source, it will disintegrate and finish, and you think maybe it is offering protection, yet it has already finished. So you need one with longer half-life to continue being there always, to continue producing the rays, the radiation here, to keep the building safe. All right, so now we are saying that now we move to safety precautions when handling radioactive substances. So we are saying ionization or ionizing radiation can damage or kill cells, or if changes take place in the DNA in the nucleus of the cell, cause mutations of genes and lead to cancer. Therefore, people who work with radiation must take safety precautions. So guys, what is being said is this, that radiation that can ionize is able to damage or kill cells, or even bring about mutation or change in DNA. So if the DNA stands for deoxynucleic acid, which is the main component that determines the makeup of a human being. So now, radiation can change this makeup. And if this makeup has been changed, that process is what we call mutation of genes. And the mutation of gene can even bring cancer, meaning the program of how genes work can be confused, and in some cases it can lead to cancer. So we are saying, therefore, people who work with radiation must take safety precautions. Yeah. So those who work with radiation should take a safety precaution, which are: number one, use sealed containers. So they must use sealed containers always to keep radioactive material. So we are saying the container should be made from lead. The same container where they are storing radioactive material should be made from lead, especially if using beta or gamma radiation. Yeah, if they use gamma ray or beta, they need lead so that it can stop radiation from leaking out. Again, they're saying the person should also wear a lead apron. So these people who deal with this should also wear aprons made of lead. Then number two, use tongs. So instead of holding directly, you use tongs, like big fork, spoon, long ones, so that radiation is far from you. So use tongs to handle the radioactive substance and stand well back. Well back meaning at a good distance from the radioactive source. Then three, display the warning sign. So always there's need to display the warning sign which tells people to say there is radiation. So we are saying always display the hazard symbol or warning sign to warn of possible dangers of radioactivity. So this is the sign which they use. Whenever you move into building places, when you find this sign, they're telling you that be careful, this place you have come to contains radioactive substances. So when you use this one, people can be aware and can take precautions. Then number four, wear a radio or a radiation badge. So there are certain badges that are worn that are used to measure how much radiation a person has accumulated, especially those who work in places of radiation. So we are saying the badge will show the amount of radiation that you have actually received. The badge can also be developed to show the amount of exposure to radiation that the user has had. So this badge, when you wear it after some period, it should be taken to measure how much radiation has been coming to you. And if it is noticed that it is too much, then you can be stopped from working in that place where radiation is produced. That way the person is protected. Then 5, minimizing exposure times. So don't take time in places where there's radiation. So we are saying keep the exposure time to radiation as short as possible. This is seen in hospitals when x-rays are being taken. So when a person, for example, is undergoing x-ray, they don't take long to avoid a person accumulating more radiation. Then 6, no eating or drinking. So you shouldn't be drinking or eating at those areas with radiation. We are saying alpha particles cause damage if they are ingested. When you eat alpha particles, they cause damage when ingested or eaten or drunk. Always wear a mask to prevent inhaling, that is breathing in of radioactive dust. So when you are dealing with radiation, you should also wear a mask to avoid inhaling radioactive dust because it is harmful. Then let's look at also dangers of radiation. So we are saying radiation alpha, beta, gamma can cause the following to human being. Number 1, they can cause damage to living cells. Number 2, they can cause genetic changes in living cells, which is a mutation. Number 3, they cause cancer. Number 4, they kill vegetation, fish, and animals. These are the dangers. Let's look at management practices which safeguard the environment from radioactive contamination. So these are practices with the management of radioactive contamination. The people that work with radiation, how they should manage it to safeguard the environment. So it's in this way. So there is no control on natural sources of radiation. So natural sources of radiation, we cannot control them. However, efforts can certainly be made to lower down radiation from man-made sources. Some of these are to avoid the nuclear explosion. So we should avoid the nuclear explosion. Then 2, minimize production of radioisotopes. So people that make radioisotopes should stop or minimize. Don't make too much. Then 3, extreme care should be exercised in the disposal of industrial wastes containing traces of radioactive or radionuclides. So when you are disposing of those materials containing some radioactive materials, there must be seriousness in disposing those. Then 4, nuclear medicines and radiation therapy should be used only when absolutely necessary and with well considered doses. So for example, when a person is suffering from cancer, they need to kill those cancer cells, then what should happen is they should take much care. They shouldn't expose the person to much doses of radiation. They can only do that if it is really the only solution which is there. Otherwise, at all costs, radioactive radiation shouldn't be the first thing to consider, but it should be the second when treating certain situations. Alright guys, thank you for watching. We have come to the end of this video. So for those wishing for online tuitions, you can join. The number is 0977 92 4175. So thank you for watching, and see you in the next lesson. As for now, bye, and please, peace.